Starting chapter 6, when you get to 6.3 and 6.4, it kind of changes gears, and we're going to be talking about vectors. So we'll start with the little clip. You may know the clip that I'm about to show you. Let's see. It starts off really quiet, so just make sure that you're listening. I can never see. So get your popcorn out.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
Okay, and this is also the part of class where I confess I've never seen Despicable Me. I'm not missing out? Okay, I get mixed reviews. But that guy says two really important things about vectors, and some of us are more familiar with vectors than others. Usually in math class, we all kind of come with the same information because we took the same classes, geometry, algebra 2. Some of us took algebra 3 leading up. But those people who have taken physics, this class has a lot. Excellent. So you guys have already covered vectors, right? So today I'm calling it like Vectors 101, and it's like all the basics of vectors. So my people in physics are going to be like, yep, got it, good. And then some of us are going to be like, wow, this is a lot of new information. So you just got to kind of figure out where you are and how much you'll need to put into studying information about vectors. We may notate things a little bit differently in mathematics than maybe you did in physics, so those will be things that my physics people can look at. But I think we could all fill in the first two blanks. A vector is a directed line segment that has what? Direction and magnitude, yeah. It's a directed line segment. It has magnitude, it has direction. Now we are going to be fixing our vectors to a coordinate plane. So they'll have like a start point and an end point. I'll just draw an example of what a vector could look like. So here could be my initial point, here is my end point, and you're going to see that the vector is drawn with an arrow. So the arrow tells you like from which point you started and which point you end on. Okay, so you're ending on the arrow point, and that way you get the right direction. Because if we went the other way, that would be a different direction. But don't think about it like a ray in geometry. A ray with an arrow out there would like keep going forever. This is a line segment, so it actually stops right there at that end point. So does anybody know what the phrase magnitude means? Magnitude represents size. Okay, it's the size of the vector. In mathematics, we might refer to the size of a line segment as its length, or we could say a distance. Okay, so all three of those words would be synonymous with magnitude, but you're going to hear me always talking about magnitude. So what I want you to be thinking about is magnitude is length, magnitude is distance, magnitude is a measurement from one point to the other. And then anything about direction that you'd like to say? What does direction represent? Yeah, obviously direction. So mathematical terms that we can use for direction would be words like slope. So I have that image of that vector up here. I could have this vector, and it has a different direction because it has a different slope. If we're thinking about it on a coordinate plane, it's much steeper. Or we could have vectors that are pointing down, so then of course we have like a negative slope. And we also sometimes refer to direction angles. So we're going to see that at the end of our notes today. But slope, angles, those kind of words mathematically are going to represent our direction for our vectors. Okay, next up is equivalent vectors. It says they have the same some things. What's going to be the same for our equivalent vector? Same magnitude, same direction. Yep. So at the end of the day today, when you leave the room, you should be able to say vectors have magnitude and direction. They are equivalent if they are the same magnitude and same direction. So this doesn't mean that they have to be like the exact same vector in the exact same location. They could be at different places on the coordinate plane. They just, in those different places, have to be true. They have the same direction and they have the same magnitude. Now, we have an example that we're going to put off to the side, so leave a little bit of space for that. But if like below same magnitude and same directions on your note sheet, if you want to do some examples and some non-examples, you could draw out a few of those real quick. Okay, so an example of equivalent vectors. These look equivalent to me because they appear to be the same length. If I got out my ruler and measured them, hopefully I drew them accurately. They're the same length. And then they're also parallel, so they have the same direction, okay, because they're the same slope. Non-examples of equivalent vectors. If I draw something like this, they might be going in the same direction, but they have different magnitudes, so they're not equivalent. Or I could draw something like this, where they might be parallel, but they're not going in the same direction, they're going in opposite directions. And of course, you could have some that are going like totally, skew opposite each other, non-parallel, whatever. Okay, so my example, this is, I don't know why, it's probably because of our new computers, they sometimes print funny, but this example didn't print on your sheet. So just kind of be aware, if you want to add it off to the side there, that would be great. If you have some questions like this on your homework tonight, it's going to ask you to show that two vectors are in fact equivalent. So U and V. Now, one thing to notice, the way that I have this on the screen, and you'll see this going forward in the other examples, when the book or I on like a quiz or a test am talking about a vector, that letter usually gets bolded, and so the bold means vector. But when you're writing them out, you don't have to worry about making the letter bold. You could just call it V and U. Okay, let's talk real quickly about those two vectors that you're seeing up there. If you want to sketch them, you certainly can. If you're just eyeballing it, do they look equivalent? They look like they have the same magnitude and the same direction. Eyeball, yeah, it looks like they're going to be parallel. They're never going to cross. And yeah, it looks like they're about the same length. But we're mathematicians, and we're being asked to show that they're equivalent. So we need to show that they have the same magnitude and direction. Anybody got any ideas on how I can show same magnitude or direction?
Distance formula for magnitude.
Okay, we could do distance formula for magnitude because we have start and stop points. Okay. Now, you could certainly use the distance formula, but I am going to ask you if besides the distance formula, there's another way to calculate the distance. It is the distance formula. It's going to be my shortcut. The Pythagorean theorem. I mean, the Pythagorean theorem is essentially the distance formula, right? D squared equals the difference of the x's squared plus the difference of the y squared, and then you square root both sides. So I'm going to say it would be just as fast if I did Pythagorean theorem for these. So I could say make right triangles. This side has length 3. This side has length 1. So for the magnitude of u, that would be the square root of 1 squared plus 3 squared, because 1 squared plus 3 squared equals c squared, square root both sides. Okay, so that's the square root of 10. And then I could do the same thing for this other one, v. Okay, the magnitude of v. And this one looks to have a distance of 3 and 1. So, of course, I'm going to get the same answer, right? 3 squared plus 1 squared equals the square root of 10. Okay. So that's the same. Now, if you calculated full distance formula, you'd get the same answer, right? Difference of the y's and difference of the x's would be 3 and 1. Okay, so we've proven that they have the same magnitude. How could you show that they have the same direction? Dylan? Yeah, do the slope. Now you could do change in y over change in x. You could do that through the slope formula, y minus y over x minus x. Or, we already kind of know what the changes are, right? Think about slope. Another word we use for slope is rise over run. So I like this method because then I can use it both for the Pythagorean theorem and for my slope, like when I calculate those distances or draw those right triangles. So the direction of u, rising 1, running 3 is 1/3. And of course, on the other one, the direction of v is also 1/3. And that's the same. So I've proven that they are equivalent. Just remember, like, when you're doing your homework, don't take the shortcut and eyeball it, right? You should prove it, show whether or not they are equivalent. Okay. Next up, we're going to talk about standard position vectors. Now, a lot of what we do in vectors is going to be similar to some of the work we did back in Chapter 4. Chapter 4 was the first chapter we did when we came back, all that trigonometry. And back in Chapter 4, we had angles in standard position. So it was like we were fixing all angles. They would have an initial side on the positive x-axis, and then the terminal side would open up anywhere in the 4 quadrants. And I could do like rotations and counterclockwise and clockwise, right? Those were always angles in standard position. Now we're going to be talking about a vector in standard position. A vector is not a full angle. It doesn't have 2 sides to it. It's just one directed line segment. So what the key here for a vector in standard position is its initial point is at 0, 0, which is the origin. So we, as mathematicians, would like our vectors to be in standard position when we work with them. That just makes everything a little bit easier because I instantly know 2 parts of the vector that are really important to me. That's the horizontal part of the vector and the vertical part of the vector. We saw why those are so important on the last slide. If I know the horizontal and the vertical part of the vector, then I can calculate their magnitudes, the Pythagorean theorem, and I can calculate their directions with slopes. So in standard position, we create something called a component form. And component form is the form of the vector that shows the really 2 important components, which happen to be horizontal and vertical components. Those people in physics, you guys know this. Okay. So if it's not already in component form, you might be given information like an initial point. Let's say our initial point is at x sub 1, y sub 1. And you might have a terminal point, your ending point at x sub 2, y sub 2. So we're going to create something called component form. We're going to call that vector v. And this component form is going to represent that vector in standard position, where this initial point doesn't have to be at 0, 0. But if I change it into component form, then I could think about it like it was at 0, 0. So to go to component form, we're going to introduce our vector bracket. It's like the angled bracket. I feel like the little vector guy in Despicable Me was going like this. So that always makes me think of the little. So we're going to vector kind of stuff to help you remember. Don't draw parentheses. And what you want is your horizontal component right here. So you want the change in x's. The one thing you'll have to be really careful here is the order matters. You have to do the terminal minus the initial so you get the correct direction for your vector. Okay, so start at the end, subtract the beginning, and then that'll give us our horizontal component. We'll also need our vertical component, y sub 2 minus y sub 1, and close it with an angled vector or bracket. Some of you may wish to write this down, terminal minus initial, somewhere in that notes page. So you remember, it is important that you do terminal point minus initial point. Okay, now obviously in our example we're going to have numbers there, so we're actually going to be able to subtract x sub 2 minus x sub 1, and we'll come up with a single number, and that's really what component form is. Component form is the vector v as v sub 1, v sub 2. And if it was like vector w, we call it w sub 1 and w sub 2. So this is the real component form. And it's made up of two components, the horizontal component and the vertical component. Just like an ordered pair, horizontal comes first, vertical comes second. And then we can do a whole bunch of stuff. Now that we put it in standard position, if it's in component form, then we can find a whole bunch of stuff really quickly and easily using v sub 1, v sub 2, horizontal component, vertical components. So we're going to talk about magnitude for all vectors in standard position right now. I'm going to draw a picture of a vector in standard position. So it would start at 0, 0. It could go anywhere. I'm just going to draw vector v over there in quadrant 1 somewhere. And we're interested in its magnitude, which is its length. Mathematicians have a special notation for this. So this is vector v. If I want to say that I'm interested in not the actual shape vector v, but I want the distance of vector v, then I would use double-sided vertical bars. They look like absolute values, but there's two of them. So that is read as the magnitude of v. Is that something that you ever saw in physics? No. Okay. So it's just the mathematician shorthand version of magnitude, right? So we're going to write a formula for magnitude of v for all vectors in standard position in component form. And again, a lot of this is going to go back to chapter 4. If this is vector v starting at 0, 0, and the vertical and horizontal components are v sub 1, v sub 2, then I know v sub 1 and v sub 2 to calculate the magnitude, just like we did on that equivalent vectors. Let's do Pythagorean theorem. So the magnitude squared is equal to v sub 1 squared plus v sub 2 squared, and then I'll square root both sides. So going forward, you should know this fact. The magnitude of a vector in standard position, in component form, is the square root of v sub 1 squared plus v sub 2 squared. Okay, so let's look at the example off to the side. You are given 2 points, and you want to get component form and magnitude, right? Okay, so we want to get the component form, v sub 1, v sub 2 with the angled brackets, and we want the magnitude, which is represented like this, the magnitude of v. So in component form, if I am given 2 points, initial and terminal, do terminal minus initial for the x's, terminal minus initial for the y's, and that'll give me my component form. So v equals, should I do -2 or -7 first?
-7.
-7. Okay, terminal, so this is x sub 2, y sub 2. -7 minus -2, 9 minus 3. My component form is -5, 6. Got the first part of my answer. And now I want to find magnitude. So I'll do the magnitude of V is equal to the square root of horizontal component squared plus vertical component squared. The math isn't really too terrible here in vectors. It's just that you know what to do. Remember, if either component is negative, when you square it, it will be positive. Never should you ever have a negative down in here at the end. So square root of 25 plus 36, the magnitude of V is square root of 61. If I could simplify the square root of 61, like look for a perfect square, I would. I probably wouldn't put it into my calculator and get a decimal, only because if you're going to use it for something later, you would want an exact value. So I'd just leave it as square root of 61. How's everybody doing with this vectors work? You doing okay? Anybody got any questions, clarifications they'd like made? Do you recall this from geometry at all? You did a short stint on vectors in geometry. Anybody? Anybody? Some people maybe. Okay, now we're going to talk about, what is it, the unit vector? Okay. The important part about a unit vector is the word unit. So like understanding when you read things in math and something's described with the adjective as a unit vector or like the unit circle, unit implies one unit, right? So here, if we're talking about a vector that's a unit vector, it's going to have a magnitude of 1. In the unit circle, that was always the circle that had a radius of 1. So we see some connection there for the word unit. Are all vectors going to have magnitudes of 1? No, we just found one that had a square root of 61, right? That's not 1. So it's probably, you're probably thinking like, probably few vectors have magnitudes of 1. So I'm going to change it to a nicer number. Suppose I know my vector has a length of 5. And I want a vector to be going in the same direction as that vector, but instead of having a length of 5, I want it to have a length of 1. What are some mathematical things we can do to change the size of that vector? Shrink it. How are we going to shrink it? Scale it, multiply it, divide it, right? So think about like in geometry, you would have like big triangles and you would make them small or larger. You would have a scale factor. So here you should write down, essentially, I mean, you're using a scale factor of 1 over the magnitude, but that's the same as dividing by the magnitude. So I just say divide by the magnitude. Whatever you do for yourself to like, tell yourself to pay attention, study, know, be aware, do that. Star, circle, highlight, bubble, whatever it is you do. This is something that escapes a lot of people. They get to the quiz on Friday, they get to the test, and they're asked about a unit vector, and they just don't know what a unit vector is, and they don't know how to get a unit vector, so they really can't do anything. But it's not hard work, it's just understanding a unit vector would have a length 1, and we're going to scale it back. So we're going to divide by the magnitude. So in the example, we have a vector v. It is in component form, 7, -3. It's got the angled brackets. So this is v sub 1 and v sub 2. And we want to get a unit vector So we would like it to go in the same direction as this vector, but have a length of 1. Well, first I want to figure out what is the length of v, or the magnitude of v. Well, that would just be the square root of 49 plus 9, which is the square root of 58. So I can see v isn't a unit vector by itself. Square root of 58 is more than 7 but less than 8. So in order for me to find my unit vector, we said above, for the unit vector, take the vector, take the vector v sub 1, v sub 2, and divide it by its magnitude. So I'm going to call it u, because it's going to be my unit vector. And I'm going to take 7, negative 3, and divide by square root 58.
So is it not a problem that there's a square root?
Well, yeah, there is a problem. Okay, so on the back side, when we flip this over in our notes, we're going to talk about scalar multiplication, which that's essentially what we're doing right now, right? Multiplying by the scalar, 1 over square root 58. So basically, scalar multiplication, we've done it before with matrices back in chapter 8. It just applies to everything, right? So I could rewrite this as then 7 over the square root of 58 and negative 3 over the square root of 58. But like Liam said, we should always leave our answers in the best looking form that mathematicians like to see it, which is to rationalize your denominator. So I would say my unit vector is 7 square root 58 over 58, negative 3 square root 58 over 58. Now, some of you probably don't have to write out the middle step of that, right? You just know, like, if square root 58 is in the bottom, you're going to put it in the top and have 58 in the bottom. That's fine. But yeah, you should rationalize that. Now, if I took the time, and I'm not going to do it, but if I took the time to check, I could figure the magnitude of u, which would be the square root of u sub 1 squared plus u sub 2 squared, which happens to be these radical looking things. And in the end, it would equal what number? 1, because I found the unit vector. So if you're ever interested, like on a quiz or test, you're not sure if your answer is right, but you've got extra time, you could just do that magnitude work for your answer, and it should equal 1. Then you know it's right. Okie doke. Okay, any last clarifications you want on side 1? Vectors 101. Anything you're dying to know? Okay, let's flip it over. So vector operations, we're going to talk about scalar multiplication, addition, and subtraction. There's a whole bunch of properties that you can look up on page 421 if you're interested, but I'm not going to take the time to go over them. They're kind of intuitive, okay, but if you're questioning, you can look at that. Scalar multiplication, we've already talked about, right? If you multiply by a scalar, you multiply through to all components. So in our component form, we have a horizontal component v sub 1, vertical component v sub 2. We multiply everything by the scalar. One important thing to note in here is if your scalar is negative, then the vector is going to change direction. So if you multiply both the horizontal and the vertical component by a negative value, they both change signs, and then your vector isn't going in the same direction that it used to. It's going in the opposite direction. But the math for these vector operations is really easy, right? Just distribute that scalar. And addition and subtraction, the math part's really easy. If you're adding or subtracting two vectors, add the horizontal components, and then add the vertical components, and that's your new vector. Same thing for subtraction. What I want you to be thinking about is visually, what does your new vector mean? And that's what this fill in the blank stuff I'm going to show you in the example when we have actual numbers. but I'll show you what this actually means. So geometrically, what's happening with the vector addition is you're going to put the initial point of the second vector at the terminal point of the first vector. Put the initial point of the second vector, terminal point of this first vector. If I were putting that in my own words, it's like build off of where you stopped. Connect the dots. You drew one vector, start right there, draw another vector. Geometrically, it's essentially this, or subtraction geometrically is essentially the same thing. The only difference here is that when you're doing your second vector, you're subtracting it, which is to put a negative scalar in front of it, so it goes in the opposite direction. So you should go in the opposite direction for horizontal and the opposite direction for vertical, and that would be subtracting two vectors. Now, the last thing there for adding and subtracting is how the book will sometimes refer to the answers of vector addition and subtraction. They call it the resultant vector. So that's a good one to like make sure you read over a few times. Sometimes when you get to directions and the book is saying something like give the resultant vector, and you're like, what the heck am I supposed to be doing? It's just asking you to add and subtract. So resultant is just the answer to adding and subtracting vectors. Okay, so we'll do the examples over in that big box off to the side. I'm going to do A with you, and then I'll let you and your pod members do B and C on your own. But I want to first talk about A in terms of the geometric property of it, right? Okay. So mathematically, this should be pretty easy for everybody. If I want to add U and V, add the horizontal components, 1 plus 3, and then add the vertical components, 4 plus 2. So the new vector, the resultant vector, is 4, 6. So that's easy math. What the heck does that mean? I'm going to sketch myself a little coordinate plane. Well, I'm starting with U, so I would sketch U, which is in component form 1, 4, so I'm assuming it's in standard position. Start it at 0, 0. And go right 1 and up 4. So there's U. Just follow its direction and magnitude. Addition says if you're adding V to U, put your initial point for V not back at 0, 0, but put it at the end point of U. So now I'm going to start V from that point 1, 4. And I'm going to go right 3 and up 2. So I'll go right 3 and I'll go up 2. So there's V. And then this vector, 4, 6, to go right 4 and up 6, represents the vector with the shortest distance from the initial point of U to the terminal point of V. So like ignore all your turns when you were adding and subtracting. It's straight from your initial to your terminal point of all the vectors. Okay? Okay, you guys go ahead and try B and C, and if you want, try to sketch B if possible. I'll put my answers up here in a little bit. only two answers for B and C up on the board if you just want to check your answers. B should be the vector in component form, so you should have the angled brackets, -2, 2. And C is -7, 2. I just want to real quickly show you B visually so you can see, like, what does the answer -2, 2 mean? Well, again, I would start with my first vector, which is U, so we already know that's right 1 up 4. Okay, there's U. This time, I'm going to build V off of that terminal point, but instead of going right 3 and up 2, because I'm subtracting, it would be the opposite for both of those. So now I'm going to go left 3 and down 2. So count left 3 and down 2. There's my V. And then again, the resultant vector, -2, 2, is the shortest distance from the starting point of U, the very first vector, to the end point of your second vector. Okay, so there's U minus V. So visually, that's the vector that you're finding. Of course, there's some stretch to our vectors because we have a scalar there, 2U and 3V. Some of you may do better if you write out 2U and 3V first. So 2U would be what? 2, 8. And a 3V would be 9, 6. So if you find it helpful to list those first as the scaled vectors and then do the subtraction, you could do it that way. Okay? You know, vector operations, I'm hoping everybody gets 100% on those questions. The work shouldn't be hard. Okay? And I don't think I asked you to sketch it. I just want you to be aware visually, because that's when we would use vectors, when we want to see it. Okay, next up are standard unit vectors. That word is popping up again, that adjective, unit. What does unit mean? Has a magnitude of 1. So we already know about unit vectors. Unit vectors have magnitudes of 1. What are standard unit vectors? Well, the standard unit vectors kind of describe the two directions that we can move for a vector. The two directions we can move for a vector are in that component form, horizontal and vertical. So imagine a vector in standard position. That means its initial point is at 0, 0. If it were a horizontal standard unit vector, what would its component form be? Horizontal unit vector. Where would be your endpoint? 1, 0. So I is the vector in component form 1, 0. This is the horizontal unit vector, essentially. It's going horizontal 1 unit. And then J represents your vertical unit vector. What would that component form look like? 0, 1. Now that would be going right and up, I and J. If you want to go the other directions, left and down, you would need to put negatives in front of them, right? But so you only need 2 standard unit vectors, 1 for horizontal and 1 for vertical. Now, the I's and J's sometimes get people who aren't familiar with vectors. And what I want to be really clear about is there's not a lot of math going on here. When we introduce the I's and J's here, it's just another way to rewrite the same thing. So underneath that it says you're going to use these standard unit vectors to rewrite a vector as it's called a linear combination. A linear combination of the vectors I and J. So linear combinations have 2 terms that are being added. And so, like, a key word for you to look for on quizzes, tests, and homework would be like this phrase. If it asks you to write it as linear combination, it wants you not in with the angle brackets in V sub 1, V sub 2. It wants it with I's and J's instead. So how do you change it? If you have component form, V sub 1, V sub 2, to change it into linear combination, it's going to look like V sub 1i plus V sub 2j. There's no bracket. It's just the two terms, the I and the j, that are being added together. Your horizontal component goes with I, your vertical component goes with j. So it's just another way to write the same thing. In that example then, if they give me 2 points for vector u, and they want me to write linear combination, I know I want my answer to be V sub 1i plus V sub 2j, but I first have to figure out what V sub 1 and V sub 2 are. So I could do my component form. Was that terminal is -3 minus 5 and -1 minus 2. So the component form for that vector is -8, -3. And all I have to do to get linear combination is rewrite it with I's and J's, take away the brackets. So my linear combination is just -8i minus 3j. That's my answer. I didn't do any math to get there once I had component form. It's just changing component form into another version. It means the same thing. So like you'll see on your homework tonight, some of them will be in component form, some of the vectors. Some of the vectors they'll give you in linear combination form, but you know what the horizontal and the vertical components are. So you can figure out V sub 1 and V sub 2 from either one. Okay, just really quickly, you don't ever have to do this work, but I want to show you why this linear combination thing works. If my vector V is -8i minus 3j, that's -8 times 1, 0 minus 3 times 0, 1. I just substituted in my standard unit vectors. Then I have scalars, so I would distribute my scalar, -8, 0 minus 0, 3. Sorry, I left it as minus, so it should be +3. And then if I subtract those two vectors, I'm going to get -8, -3. So by substituting into standard unit vectors, it is the same thing as component form. But you don't ever have to do this work. It's just always true for the I's and the J's. Okay, last thing is direction angle. So sometimes we can describe the direction of the vector as an angle, and this angle is the angle between the vector and the positive x-axis. Well, gosh, that sounds really familiar. That's like an angle in chapter 4. Positive x-axis, vector somewhere out in space, right? If I draw a picture of that, there's vector V. I'm interested in this angle right here, positive x-axis and the vector, and that could be in any quadrant, right? So it could be anywhere. And then I know V sub 1 in component form, and I know V sub 2. Well, how can I find theta? Tangent. The tangent of theta, if you know component form, is equal to V sub 2 over V sub 1. V sub 1, opposite over adjacent, y over x. And I usually know that as theta equals the inverse tangent of V sub 2 over V sub 1. Either one is fine, whichever one you choose to memorize. If you don't memorize it, draw a picture and you'll be able to get it. But there's two things to be aware of. Okay. you've got to consider two things. Your answer should be between 0 and 360 at the end. So it should be positive, and it should be within one revolution of the circle. And you have to be aware of what quadrant it's in. Okay, so make sure that you highlight that portion of the notes. So I'm going to go through really quickly these last two examples. We're going to find the direction angle for these two vectors. The first one's given to me in component form, so I know v sub 1, v sub 2. Theta is the inverse tangent of 4 over 3. You can set your calculators if you want to degree mode. And when you do that, you get, I think this one is like 53.1 degrees. Now, that angle is between 0 and 360, right? Does it correspond with the quadrant in which the vector lies? Well, where is 3, 4? Quadrant 1. Is 53.1 an appropriate angle for the vector in quadrant 1? Sure. So this is my answer. In this problem, I would do theta equals the inverse tangent of negative 10 over negative 3. And my calculator is going to give me an answer 73.3 when I do that. And that angle is between 0 and 360. Does it correspond with the quadrant in which negative 3i minus 10j lies? No, that one, left 3, down 10, is somewhere in quadrant 3, which that angle from the positive x-axis to that vector is not 73.3. How do I get the actual angle? It's like a reverse reference angle. So 73.3 is that angle from the negative x-axis to the vector. So I would do what? Add the 180. It should be between 180 and 270, right? So that comes out to what? 253.3 degrees. Now, if you're in quadrant 2 or quadrant 4, when you put in your inverse tangent, instead of getting a positive angle back out, it'll give you a negative angle out. And then if you're in quadrant 4, you want to subtract from 180. Or sorry, if you're in quadrant 4, you want to subtract from 360. If you're in quadrant 2, you're going to subtract from 180 because you're like doing a reverse referencing. Your homework's on your gold sheet, so work through those problems, and we'll talk more about vectors tomorrow.